In this video, we're going to take a look at transformations of functions. Now, the basic idea of this section is to start with a base function, or what some books would call a toolkit function. And then we're going to move it, stretch it, flip it, adjust it. And that moving, stretching, flipping, adjusting, all is going to correspond to different algebraic operations. So let's start with some basic base functions or toolkit functions. The first base function that we're going to look at is the idea of a constant function. That's the function where you input any value x and you get out a constant number c. Generally, that's going to be a real number. For instance, if c was equal to 3, we would get the graph of this. So these constant functions correspond to horizontal lines. They essentially correspond to the horizontal line because all output values, all y values, are going to be the same number c. Our next base or toolkit function is sometimes called the identity function and sometimes called a linear function, our base linear function, I should say. And that is f of x is equal to x. So whatever you input, you get that exact same value as the output. That's going to generate a line through the origin whose slope is 1. So the rate of change is always 1. And every point on that line is going to have the form x comma x. In other words, the input value is the same as the output value. That's one of the reasons why this is often called the identity function. It's linear, it's our base linear function because it produces a line. Another base function, standard base function or toolkit function is f of x is equal to x squared. We call this quadratic. X squared produces a quadratic function. So this is our base quadratic function. And it gives us a parabola pointed upwards. Another base function is the cubic function. F of x is equal to x to the third. And it gives this shape. It's not a straight line, but you can see it goes through the origin and then curves up and gets very, very steep as you move towards the right, gets very, very steep decline as you move towards the left. These aren't the only base functions or toolkit functions we'll see. Another base function is the square root function. F of x is equal to the square root of x. It starts at the origin. Notice that we are not able to plug in any negative numbers because we have square root of a value. We don't want to have square root of a negative. And so it starts at the origin, and as we move towards the right, it grows, but pretty slow as we move out. Cube root function, f of x is equal to the cube root of x, looks like this. You can plug in negative numbers there, and we get this shape. It kind of looks like a square root, although the growth isn't quite as fast as the square root. And then it has a symmetry about the origin. We'll talk about that later. The base reciprocal function is 1 over x. As you move to the right, it approaches the x-axis. As you move to the left in the first quadrant, it approaches the y-axis. As you move to the left in the third quadrant, it approaches the x-axis. As you move towards the right, it approaches the y-axis in that third quadrant. That's the reciprocal. The reciprocal squared function is 1 over x squared. It looks like this. Notice you approach the y-axis both from the left and the right as you approach 0, and they're both moving up. Whereas the base reciprocal function, one was moving down, one was moving up. And then the last one we'll talk about in this section is our absolute value function. F of x is equal to the absolute value of x. That creates a nice V shape. Again, absolute value, whenever you plug in a positive number, gives you that positive number out. Whenever you plug in a negative number, then you get the positive version of that negative number. So if I plug in a 5, I get out a 5. If I plug in a -6, I get out a +6. Now, these are the base functions that we're looking at in this section. If you stay and look at some of the next chapters, some of the next chapters will have exponential functions, logarithmic functions, sine functions, cosine functions, tangent functions, and on it goes. And so there'll be a lot of other base functions as well that we'll see in chapters ahead. Once we have the base functions and we kind of know what those look like, then we're going to transform them. The first way we'll transform them is through vertical and horizontal shifts. If I create a new function, we'll call it, well, let me restart. If we start with a function f of x, and then I use it to create a new function, if I say my new function, we'll call g of x, is equal to f of x plus k, where k is outside, then that'll produce a vertical shift of the function f of x. If I take my new function and I take f of, in parentheses, x minus h, that will produce a horizontal shift of the function f of x. So if I want to take a base function and move it up or down, or left or right, or any combination thereof, I can do so by using the right value of h and k. Let's do an example just with the absolute value function so we know what's going on. So if I take the absolute value function and then I add or subtract a number outside of the absolute value, notice that by adding 6, I moved the absolute value function up 6 units. That's going to be the same no matter what I add. So as I add 2, we're moving it up. We can move it up. We can also move it down if I use negative k values. So I move down by using negative k values. So up and down when I add a k on the outside. Now, what if I subtract an h on the inside? Well, subtracting an h on the inside moves the function left and right. So if I do x minus 6, then I've moved this function to the right 6 units. And if I do x minus a -6, that's like x plus 6 on the inside, then we've moved the function left. And with this h and k, we can move the function up and down and left and right to wherever we want. So move the function left and right and up and down to wherever we want by just adjusting the values of h and k. Remember, positive k moves up, negative k moves down. We have x minus h, and if I have a minus h, then a positive h moves right, negative h moves left if it's x minus h. We can therefore determine how functions are shifted just by looking at this. So let's go ahead and do that. I'm going to write the answers down, but f of x, I don't even know what it looks like. Doesn't even matter what function it is. If I create a new function g of x by taking f of x minus 7, what does that do? G of x by taking f of quantity x plus 3, what does that do? G of x is equal to f of x minus 2 plus 10. What does that do? Again, let me write it down. So let's do this. The minus 7 here is outside of the f of x. So that is going to be a vertical shift. And since it's a minus 7, we're going to be shifting down 7 units. So that's a vertical shift down 7 units from f of x. So down 7 units from f of x. Now the next one, we have x plus 3 on the inside. This is where people often get things messed up. It's a horizontal shift. Now it's actually left 3 units. Okay, because remember, we have x minus h as the formula. If I did x minus h, then h here would have been a -3, and that's a left shift of 3 units from f of x, obviously. And then like with g of x, we can combine, that's a vertical shift up 10 units along with a horizontal shift of right 2 units. So we're going up 10 units and right 2 units. I won't do any more than that. So there we go. Up 10, right 2. Again, I don't even know what my original f of x was, but I know that's what's going to happen. That's the graph that's going to be created. It's going to look like f of x shifted down in the first one, shifted left in the second one, shifted up and right in the third one. Let's do another example, but with a specified function here. Let's look at f of x is equal to x squared. So that's my original function, which is my base quadratic function. And let's take g of x to be x plus 2 inside of parentheses squared, and then plus 5. And then let's let h of x be x minus 1 inside of parentheses squared plus 8. And ask ourselves, how is g of x been shifted from f of x? How has h of x been shifted from f of x? Again, our base function here is the f of x equals x squared, which is our quadratic base function. Push pause on the video if you'd like and try it on your own. In a couple of seconds, I will show you how it's done. All right, so g of x, we have a plus x plus 2 inside of the parentheses. So, and a plus 5 on the outside. After the x plus 2 is on the inside of parentheses, then it's being squared. So a minus 2 is our value for h, and a plus 5 is our value for k. So this is shifted up 5 units. And, well, again, always have to remember it's x minus h. So that's going to be a negative 2. We're going to shift left 2 units. From our original function, f of x equals x squared. Similarly, in h of x, we're shifting up 8 units. And in this case, since it's x minus 1, it'd be right 1 unit from my original function of f of x equals x squared. By the way, if you ever have a question about being right on your shifts, then you can obviously graph it on your calculator or on Desmos and see how it goes. Actually, let me do that real quick. All right, so here's my base quadratic function, and the g of x here is going to be x plus 2 in parentheses quantity squared, and then plus 5. So like we said, it should move left 2 units and up 5. So the new sort of bottom of the parabola should be at negative 2, 5, hopefully. And sure enough, if I highlight that, I get exactly what I'm looking for. So I've moved this thing left 2 and up 5. H of x is equal to quantity x minus 1 in quantity squared plus 8. So we should move it 1 to the right and then 8 units up. So our new sort of bottom of the parabola should be at, 1, 8, which would be about right there. And sure enough, there it is. Move right 1, up 8, and then we get to the new parabola. So this red one is just the black one shifted right 1 and up 8. So that's a good check. We can always graph these things, not just with Desmos, but with the TI-84 as well. And you should know how to graph with the TI-84 if you're using that for your class. If you don't, then there'll be a companion video somewhere on the website that shows you how to graph with the TI-84. Now, we did vertical and horizontal shifts. Now let's do vertical and horizontal stretching. So we're going to start with a function and have a positive real number. We'll call it a. Then if I create a new function by taking a times f of x, We'll call that new function g of x. It will stretch out f of x vertically by a factor of a. Now, what if we put the a in the inside? If we create a new function called f of the quantity ax, well, that is going to produce a horizontal stretch of the function f of x. Now, if a is bigger than 1, with the vertical stretch, it's going to actually stretch it. If a is less than 1, but between 0 and 1, then it's going to shrink. It actually works in the inverse way when I do this. If a is bigger than 1, then I get a shrink. If a is less than 1, I get a stretch. So basically, we have a vertical and horizontal stretch by a factor of a, or you could think by a factor of 1 over a, one of the two. So let's take a look at this example. We have g of x is equal to f of 3 of x. And then g of x is equal to 5 times f of x. And g of x is equal to f times 1/4 of x. I say f of 1/4 of x, excuse me. F of 1/4 times x. So how are these functions stretched or shrunk from my original f of x? Now, before I actually do this, let me just visualize this on Desmos. So what do we mean by a horizontal and a vertical stretch? So right now I have my base function f of x equals x squared. And I'm going to do a vertical stretch by a factor of a. So I'm going to take a times the quantity x squared. If I start moving this, let's say I have an a of 2. In fact, let me just use the numbers in front instead of throwing it. So what I've done is I've taken every single point on my parabola, like the point 1, 1. And I vertically stretched that out. So now that point 1, 1 has doubled its y value. So the point 1, 1 is now the point 1, 2. And the point that used to be 2, 4 has doubled its y value. And so now we're looking at the point 2, 8. That's what we mean by a vertical stretch, that every time we have a point on our original function, in this case, we've doubled the y value because we put a factor of 2 out front. If I put a factor of 3 out front, then I would have tripled the y value. So the point 1, 1 would now be vertically stretched to the point 1, 3. And the point 2, 4, we would have tripled its y value. So that's the point 2, 12 now. And if I would have multiplied by a 4 out front, then 1, 1 gets vertically stretched to 1, 4. I should have said negative 1, 1 also gets vertically stretched to 1, 4. 2, 4 would have gotten stretched out to 2, 16. And sure enough, that's where this stretched out goes. That's what we mean by vertically stretched. Now, that was a vertical stretch because all of the coefficients were bigger than 1. If the coefficient is exactly 1, then 1 times anything is itself, so I get back my original function. But what if the coefficient was like 1/2? Well, then it would have been a vertical shrink. So therefore, 1 would have shrunk to the point 1 comma 1/2 or 1.5. And 2, 4 would have gotten cut in half, and that now is the point 2, 2. Same thing if we would have cut something by a fourth, shrunk it by a fourth. Now 1 turns into 1 comma 1/4. 2, 4 turns into 2 comma 1. By the way, notice that 0, 0 did not move because if you multiply 0 by any number, it still is 0. So that's our vertical stretch and shrink. We can do the same thing horizontally, but with a horizontal, when it goes inside, what happens is that if you multiply by 2 on the inside, then it actually is a horizontal shrink of a factor of 2. Here's what I mean by that. Now my point 1 has horizontally shrunk, so the x value has changed, and it's changed to the point 0.5 comma 1. So multiplying by 2 on the inside cut all of my x values in half. That's the way I think of it anyways. And the point 2, 4, let's go up here, 2, 4, when I multiply by 2 on the inside of the parentheses, gets horizontally shrunk by a factor of 2 to 1, 4. So the x value gets shrunk there. And obviously I could have done any value. If I make a 6 on the inside, it gets shrunk by a factor of 6. Gets closer horizontally to the y-axis by a factor of 6. So 1 would have become 1/6 comma 1. Now, if our number on the inside is 1, then that's my original function. If it's something like 1/2, then it's a horizontal stretch by a factor of 2. So my 1 becomes 2 the x value doubles. Same thing with 2, 4. My point 2, 4 out here would have now become the point 4, 4. Every x value doubles. And the same thing is true if I multiply by a 1/3 on the inside. Now the x values all triple. Again, 0, 0 doesn't change because tripling 0 still leaves you at 0. So that's the idea of horizontal stretching and shrinking. Now let's take a look at example 3, where we have a function which we called f of x, and we're going to transform that by multiplying by a number either on the inside of the argument of the function or outside of the function. G of x is equal to f of 3 of x. g of x is equal to 5 times f of x, and g of x is equal to f of 1/4 x. How are those functions stretched or shrunk from my original f of x? If you want to push pause on the video, you can do that now, and I will give a couple of seconds if you'd like to do that. All right, this first one is, since it's inside, this is a horizontal. Stretch or shrink. It turns out that this one's a shrink by a factor of 3. Again, inside parentheses, it's horizontal, shrink, or stretch. On the outside of the outside of the function, I should say, then that's a vertical, in this case, stretched by a factor of 5. And then lastly, this, since it's on the inside of the parentheses, multiplying by 1/4, it's actually a horizontal stretch by a factor of, and in this case, you can either say by a factor of 1/4 or by a factor of 4. I'm not, yeah. Depending on how you think of it, it's getting bigger by a factor of 4 horizontally. That factor is also 1/4 on the reciprocal. So maybe we'll say stretch by a factor of 4, or you can think of it as a factor of 1/4. But there you go. That's the whole thing. Let's take a look at our function f of x is equal to the square root of x. That's our base function. And let's determine how these two functions are stretched or shrunk from f of x is equal to the square root of x. We'll just say stretched slash shrunk by a factor of, and then whatever the number is. So our base function, once again, is f of x is equal to square root of x. How is g of x stretched or shrunk from that? How is h of x stretched or shrunk from the f of x? Push pause on the video if you'd like to try it on your own. All right, the first one, g of x, since there's the 9 on the inside of the square root, that is a horizontal stretch or shrink. Technically, it's by a factor of 9. It's actually a shrink by a factor of 9. And for h of x, that is a vertical stretch slash shrink by a factor of 5. And again, in this one, technically it's a shrink. You're getting closer to the y-axis. In this one, it's a stretch. You're getting further away from the x-axis. Your y values are all being multiplied by 5 for h of x. Your x values are all multiplied by 1/9 for g of x. That's how these horizontal stretches and shrinks work. When we were stretching horizontally and vertically, we forced the number out in front to be a positive number, if you recall. The A we used was forced to be positive. Well, what if we put a negative out in front of a function? Or what if we put a negative in the argument of our function? Well, if I start with a function f of x, and I create a new function by taking the negative of f of x, that will flip my function's graph across the x-axis. If you think about it, every positive y value now becomes a negative y value. Every negative y value now becomes a positive y value. So that's going to flip it back and forth across the x-axis. On the other hand, if we take a new function, g of x, and we set it to f of negative x, that'll turn every x value that we had that was positive into a negative, and vice versa. And so that's going to produce a flip across the y-axis. Again, from our original function. So when you put a negative in front of the function, it produces a flip across the x-axis. When you put a negative in front of the x inside the argument of the function, it produces a flip across the y-axis. And that flip is called reflecting about the x-axis or reflecting about the y-axis. Let's take the square root function and see how it looks with the square root function, this flipping across the axes. So if I put a negative in front of my square root of x, I take negative square root of x, it's going to take my original square root, which was here in the black, and it's going to flip it across the x-axis. So every point that had a positive y value, like 4, 2, changes into a point which has a negative y value. It'll change it into something like 4, negative 2. So 4, 2 becomes 4, negative 2. 9, 3 becomes 9, negative 3. 16, 4 becomes 16, negative 4. By the way, 0, 0 becomes 0, 0 because negative of 0 is still 0. So a negative in front of the square root flips it across the x-axis, my original function. A negative on the inside of the square root, so the inside of the function, flips it across the x-axis. Now we're pointing this way. Now every point like 4, 2 gives me a point which is the negative x value, comma 2, negative 4, 2, for instance. And 9, 3 becomes negative 9, 3. So my new square root of negative x looks just like the square root of x, but flipped across the y-axis. So all x values change from negative to positive. That's what's going on with this reflecting about the x-axis and reflecting about the y-axis. Let's do an example. Let's determine how the functions are flipped from my base function f of x is equal to the absolute value of x. Here we have g of x is equal to negative of the absolute value of x. Since the negative is on the outside, this g of x would be flipped across the x-axis. All of the y values turn from positive to negatives. So this is a flip across the y-axis. H of x being the absolute value of negative x, that would have been a flip across the y-axis. So g of x is a flip across the x-axis. H of x is a flip across the y-axis. Now, an interesting thing happens with h of x. Let me show you that. My base absolute value looks like this. Now, if I flip across the x-axis, that's what we did with g of x. That's the negative on the outside. Then now that V shape is pointed down and sort of the tip top is at 0, 0 or the origin. So we get this V shape pointing down when I do g of x is equal to negative x. Now, what if I flipped every point across the y-axis? Notice that every point like 5, 5 has a matching point of negative 5, 5 already across the y-axis, and negative 5, 5 has a matching point of 5, 5 that's already across the y-axis. So if I flip this across the y-axis, that's what happened with h of x, I actually get the same graph back. So that's the graph of h of x, and I got that because every point in the first quadrant had a matching point in the second quadrant. In other words, we had this, what we would call symmetry for our function. So whether it was the original function, which was in black, or flipped across the y-axis, we had, again, symmetry. Sometimes that happens. Sometimes we do get symmetry with the y-axis. And that's what happened in this case. H of x was a flip over the y-axis, a reflection, right, about the y-axis, which actually produced the same graph. We can put a lot of things together as well. So we've done shifts, we've done stretches, we've done flips, meaning reflecting about the x and y axis. So we can put a lot of those things together and get some interesting functions. Let's take a look at these two functions and determine the transformation from the base function. And then ask ourselves, well, how could this graph, or how could we use the idea of transformations to graph this function? The first function I have is 1/2 x to the third plus 4. The second function I have, g of x, is negative quantity x minus 2 squared plus 1. When you go about describing the transformations, typically you work inside out. So you start with things that are inside the operation, the indicated operation, and then you work out in sort of an order of operations way. Let me explain what I mean by that. So we start with a base function. And my base function in this first case is going to be y equals x to the third, or f of x equals x to the third. I'm hesitant to use f of x because f of x is my new transformed function. So start with this base function, this x to the third or cubic function. And then we're going to multiply in front by a half. That is a vertical stretch or shrink by a half. Technically, it's going to be a shrink. And then I'm going to add 4. So then I'm going to do a shift up, vertical shift up by 4. I don't want to vertical shift up by 4 and then try to stretch and shrink, because then things get thrown off. So I do order of operations starting with sort of my inside base function, and then say, well, as I move out, what operations would I do? I'd stretch it, shrink it by a half, and then I'd shift it up by 4. Let's take a look at g of x and do the same thing. So we are going to start with the base function y equals x squared, or my base quadratic function, because we have a squared there. And then I'm going to start inside. X minus 2 is a horizontal shift, and this would be to the right 2 units. I'll just say horizontal shift right 2. And then I'd move on my next order of operations. That would be the squaring part. And then outside of that, there's a negative. And so then after I shift it right 2, I would flip that across the x-axis. Flip or reflect across the x-axis. And then lastly, order of operations would tell me to add 1. And so therefore, lastly, I do a vertical shift up 1. So if I know what my base function looks like, and we know what the base function of y equals x to the third looks like, then I would know exactly how to graph these. I could start with y equals x to the third, and then stretch it by a factor, vertically stretch it by a factor of 1/2, or vertically shrink it by a factor of 1/2. All the y values would get cut in half. And then shift every point up by 4. In this one, if I wanted to graph it, I do a horizontal shift right 2, and then flip across the x-axis, and then vertically shift it up 1. Let me just do one of these. I'll do this second one since it has more operations. So here's my base function. And what I would do is I'd move the whole thing right 2 units, like I said, if I was drawing this by hand. So I'd move it right 2 units and I'd get a parabola in that kind of spot, right? Going through the point 2, 0, and then bending up both ways. And then I would flip that across the x-axis. So I would end up getting a parabola pointing down like this. And then I'd add 1. And so my new vertex of the parabola would be here, and I'd be pointing down. Let me actually clear that other drawing. Something like this. Again, I'm not drawing it perfectly by any means because, this is not a great drawing tool. But I'd get something, I would expect to get a parabola pointing down right there, something that looks like this. And let's see what it actually does. Well, sure enough, that's what it actually does. It's a parabola pointing down. Like I said, we moved it over 2, flipped it upside down, and then moved that thing up 1. And so going through the point 2, 1, and then pointing down. That's exactly what we said with this g of x. So once I know the base function and the transformations, then I can actually graph the function as long as I know those things. Now we can do this process in reverse as well. If I look at the graph of a function, I can see what type of function this is, and then based on the transformations that I see, I can find the equation for uh, for the function based on the graph. Let's take a look at this example, example number 7. If I look at this function, it looks most like the cubic function. That is y equals x to the 3rd power. Now, if we go back to our cubic function, oops, excuse me. Let me go back to our base cubic function. Sorry, that was too many scrolls. But our base cubic function goes through the origin, and it also goes through the point 1, 1. If you plug in 1, you get a 1. That's a good indication of any horizontal or vertical stretch. But notice that as it goes through the origin, that's kind of where it flattens out for a moment. I'm going to view it in Desmos because it has a little bit bigger graph than here. So the point at which it flattens out for just a moment is the origin in my base cubic function. And then it goes through the point 1, 1. So 1 unit to the right, 1 unit up. So that's what I'm going to look for in my graph. Notice that the point at which this flattens out looks to be the point -2, 3. So we've shifted left 2 and up 3. Now, if we start here and move 1 to the right, 1 up, it does in fact look like it's going through that point as well. So the shifted 1, 1, it doesn't look like it's been vertically stretched or horizontally stretched at all. It's just been shifted left 2 and up 3. So the shift is left 2 and up 3 from the cubic function. Knowing that, I can say I'll write f of x. You could also write y. We're going to start with the cubic function, x to the third. We're going to shift it left 2. Now be careful. Remember, this is x minus h. If we go left, the h is a -2. Minus a -2, I'd probably call +2. So x plus 2, that shifts it left 2 units. Up 3 units is a +3 at the end. Therefore, I know that this function that gives me this graph is f of x is equal to quantity x plus 2 cubed plus 3. Left 2 up 3, shift from x cubed. Again, you don't have to write f of x. Some people would write g of x or h of x, whatever letter it indicates to use. Go ahead and use that letter. Let's try another. Let's look at example 8 and try to determine the equation for this function, or the equation that produces the graph that we see here. Push pause on the video if you'd like to do this on your own. I will do it in a couple of seconds. Hopefully everyone could recognize that that was a shifted version of our base function that was absolute value of x. So here's the absolute value of x. The only reason I bring this up is because notice that once again, our key point here, the bottom of this V, is the origin. And once again, we're going through the point 1, 1. We also, as you move left 1, you go up 1 as well. So in terms of any vertical stretch, I have to know that, or horizontal stretch, I have to know that. But the key point is 0, 0. That's where it's probably easiest to see my up, down, left, right shift. And then, as we can tell, it goes through the point 1, 1. Now this is pointing down. My graph is pointing down instead of pointing up, and therefore there was a flip across the x-axis at some point in time. What I would do is I would say this looks like we took the absolute value function, we shifted it right 3 units, then did a flip, and then shifted it up 4. So we did right 3 units, then did a flip across the x-axis, then shifted it up 4. There's no horizontal or vertical stretch because notice that as you move 1 unit down, you move 1 unit over. So there's no horizontal or vertical stretch that I need to worry about. That means I can take my function, again, my base function was absolute value of x. Shifting it right 3 would be an x minus 3 inside of the absolute value. Flipping across the x-axis would be putting a negative in front of the absolute value. And then shifting it up 4 would be a plus 4. As always, you could graph this on Desmos or a calculator. And if you graph this on Desmos or a calculator, you would see that this f of x does in fact give you this graph. Right 3, flip across the x-axis, up 4. Let's do one more example like that. Here we have example 9. In example 9, this is a parabola, and therefore our base function should be the quadratic base function, y equals x squared. If you want, push pause on the video and try to find the expression, the algebraic expression for the function that gives you this graph. Now, once again, the easy point to see where it's been shifted is the bottom point of the parabola. So the very bottom point of this quadratic function, which is the origin. So we'll kind of look at that, how it's been shifted. Also, if you move 1 out from the origin on your base function, you move 1 up. So you move, again, goes through the point 1, 1. So that's really all we need to know about our base function to find our function that we saw. Now the shift is pretty obvious on this one. We've taken that bottom point, we've shifted it from the origin left 1 and down 3. But here's the trick. Notice that if you move over 1 unit and up 1 unit, you do not hit a point on the parabola. In fact, if you move over 1 unit, you move up 2 units to hit the point on the parabola. This means that it was vertically stretched by a factor of 2. Hopefully that makes sense, because normally we go right 1 and up 1. Now what we've done is we went right 1 and up 2. So that is a vertical stretch of 2. Let me write that down. So we've shifted left 1 unit, vertically stretch by 2, and then we'd shift down 3. We want to do our downshift after we've vertically stretched. By the way, you could vertically stretch first and then shift left 1. It doesn't affect a lot, but that's what you're doing. The function expression would be equal to, again, I'll start with x squared because I know it's the quadratic base. And then I'm going to shift left 1 unit. Remember, that's a plus 1 on the inside. Vertically stretch by 2, that's a multiplication by 2 on the outside. and then shift down 3. That's what we get. And sure enough, if you graph that, you will find this exact graph for the function. So left 1, vertical stretch by 2, and then down 3. Okay. Now I do want to say this. The hardest part to see usually is the vertical stretch or the horizontal stretch if there is one. And I keep using the fact that our function goes through the point 1, 1 because the vast majority of our base functions do go through the point 1, 1. Constant functions are just horizontal lines, but my identity or linear function goes through the point 0, 0, and 1, 1. My quadratic function goes through the point 0, 0, and 1, 1, my base quadratic. My base cubic function goes through the point 0, 0, and 1, 1. My base square root function goes through 0, 0, and 1, 1. So does the cube root. So does the reciprocal function. And so does the reciprocal squared function. So does the absolute value function. Okay. Now these other ones will not necessarily go through those 2 points, but a lot of our base functions or our toolkit functions go through 0, 0, and 1, 1. And so if we're asked to identify a vertical or a horizontal stretch, just move over 1 and see how far up or down you have to go to get to the next point. Or move up 1 and see how far left and right you have to go to get to the next point. So that's how I always look for my standard horizontal and vertical stretches. Now that we can look at transformations of functions and figure those out, one other thing we're going to look at in this section is the concept of even functions and odd functions. A function is even if when you plug in negative x into the function, you get the same thing as if you plug in a positive x inside the function for all values of x. Now, what this means is that if I plugged in a 2 and a negative 2, they'd give me the same value. If I plugged in an 8 and a negative 8, they'd give me the same value. And what that means, point-wise, is that for each point on the right-hand side of the graph, there's a corresponding point with the same y value on the left-hand side of the graph. In other words, an even function has a graph where the graph looks like a mirror image of itself if I reflect across the y-axis. An odd function is one where if you plug in a negative x value, instead of getting the same thing out as if plugging in a positive, you get the negative of what you get when you plug in a positive. So for instance, if I plugged in a 2 and got an output of 3, then plugging in a negative 2 would give me an output of negative 3. If I plugged in a 2 and got an output of 16, I'd plug in a negative 2, I'd get an output of negative 16. And the same is true for all other x values. Now, what an odd function looks like, it looks like it is a mirror image of itself reflected through the origin. So every point which is x value comma y value, has a corresponding point negative x value comma negative y value. So that's what we end up with our even and odd functions. So the points on an even function, if I have a point which is x comma y, then it's going to have a corresponding point which is negative x comma the same y value. On an odd function, the point x comma y has a corresponding point negative x comma negative y value. Now I want to point out that not all functions are even or odd. There's lots of functions that are neither even nor odd. So there's obviously the even functions, there's obviously odd functions, and then there's a lot of other functions which are neither even nor odd. So we're going to determine whether a function is even, odd, or whether it's neither by using a couple of tools. Let's start out by using the algebraic tools. So let's determine if the functions are even, odd, or neither utilizing algebraic tools. I'll show you what I mean by that as we go through a couple of these. Let's start with f of x. So what we do to determine even, odd, or neither is we take f of negative x. That's the key thing. What happens when I plug in a negative of the x value? And then I replace this x value everywhere I see it with a negative x. And then I'll use algebra to simplify. Now I know that if I take a negative and square it, I get the same thing as a positive squared. So I know that the quantity negative x squared minus 5 is the same thing as just x squared minus 5, which happens to be the original expression for my function. So using algebra, we showed that if I plug in negative x, I get the same thing as if I plug in a positive x. That's the definition of an even function. Therefore, my original function is even. Let's look at the next one, g of x. We would do the same thing. We'd plug in negative x instead of plugging in x. And then everywhere we see an x, we replace it with a negative x. So negative x cubed plus 5 times quantity negative x squared. Now in this case, when we take a negative x and then cube it, that's the same thing as negative x cubed. But when we take 5 times negative x squared is going to be a positive x squared. So I get plus 5x squared. Now that is not my original function because the first piece, the first term, is the negative of my original function term, but my second matches up. Therefore, when I plugged in negative x, that was not equal to g of x. And also, that was not equal to negative g of x, because if I did negative g of x, then the negative would have to distribute into both terms. I usually don't write that part down. I just state that it's clear that g of x is neither even nor odd. So it's not the negative. When I plugged in negative x, I didn't get the negative of g, and I also didn't get g by itself. So g of x is neither even nor odd. Let's look at h of x and do the same thing. Plug in negative x. Now, for this one, the cube root of x becomes the cube root of negative x when I plug in a negative x. That's going to be the negative of the cube root of x, which notice is just the negative of h of x. Since h of negative x is the same as negative h of x, that is the definition of being odd. Therefore, this function, h of x, is odd. So we had one each way, where when we plugged in a negative, we got the function back. Therefore, the original function was even. When we plugged in the negative x, we got the negative of the function. Therefore, our function was odd. And when we plugged in a negative x, we got neither the negative of the function nor the function back. So therefore, our function was neither even nor odd. Oh, that's why it's spelled wrong. There we go. Hopefully that makes sense. So that's how we use algebra. We just plug in the negative x, we get back my original function. I know my original function was even. If I plug in a negative x and I get back the negative of my original function, then my original function was odd. And if I don't get either, then it was neither. Let's do one more. Let's try example 11. Push pause on the video if you'd like to try this on your own. In a couple of seconds, I will show you how it's done. Okay, in this one, this first one, f of x, what we would do to check algebraically what happens is that we would plug in a negative x. And that would give me not negative, that would give me 1/2 absolute value of negative x plus 4. We should all know that the absolute value of negative x is the same thing as the absolute value of x. So I get 1/2 times the absolute value of x plus 4, and that is my original function. So once again, when I plugged in a negative x, I got back the same output as my original function, and therefore my original function is even. For this second example, g of x, let's plug in a negative x here. That would give you a negative x minus 2 in parentheses cubed. Now that is clearly not the same thing as x minus 2 in parentheses cubed. hopefully we can see that. Just plug in any number and other than 0 and see that it gives you a different value. But also, if I would have factored out a negative, which we could have factored out a negative, I would have had to factor it out of both the x and the -2. So I would have gotten negative x plus 2 cubed. That is not the same thing as the negative of x minus 2 cubed. So that's not negative g of x, and that's not g of x. And therefore, g of x is neither even nor odd. Let's check out h of x. Plug in a negative, and you get negative 1 over negative x, which is clearly the same thing as 1 over a positive x. Notice that is the negative of h of x. Therefore, since h of negative x is the negative of h of x, algebraically, we know h of x is odd. I know on these past examples, we went even and then neither and then odd in that order on both of them. Don't get thrown off by that. Obviously, that's not always the case. But this shows you how to do this algebraically. You plug in a negative x into the function. If it's algebraically equivalent to your original function, we know then your original function is even. If it's algebraically equivalent to the negative of your original function, then we know the original function is odd. And if it's neither the same as the original or it's neither the negative of the original, then it's neither even nor odd. So that's how we can determine even, odd, or neither through an algebraic approach. The other approach would be graphically, would be trying to graph the function, and you could probably use technology to do that, and see that is the function a mirror image of itself reflected across the y-axis. If it is, then it's even. So what I mean by that, if every point on the function has a corresponding point of negative x comma y, then it's reflected across the y-axis, it's even. If every point xy has a corresponding negative x, negative y, then it's reflected through the origin, and I can see that it's an odd function. Let's go back and do those previous exercises. That is example 10 and example 11 using the graphical techniques. Here's example 10. I'll go ahead and graph these. And then, so I don't have to go back to the slides, I'll also just graph the problems on example 11 as well. We'll do them one by one, but we'll graph them and then through their graphs see if they're even, odd, or neither. I've graphed this on Desmos. Obviously, you could graph it on the TI-84 calculator as well if you want. So let's take a look at these one at a time. My first one was f of x equals x squared minus 5. For every point on the right-hand side of the y-axis? Do I have a corresponding point on the left-hand side of the y-axis that is equidistant to it? Sure enough, I do. Every point, let's say, for instance, the point 2.23607, comma 0, has a matching negative 2.23607, comma 0. So since this is symmetric about the y-axis, in other words, if I draw a line through the y-axis, the left-hand side and the right-hand side are mirror images of each other. That shows that this graph is even. So I should say, not the graph is even, the function that produced this graph is an even function. Let's do g of x next. G of x looks like this when you graph it. Notice that it's clearly not the case that it's even because there are certain points over here that do not have corresponding points over here. Also, it's not odd because a point like something over here, to be odd, it'd have to be reflected through the origin. So this 0.916, comma 4.96 would have to have a corresponding negative 0.916. It'd have to have a point over here. Negative. That's what it means to reflect through the origin. If we have a point over here, reflected through the origin, we get the point over here. That is clearly not the case. The same thing would go for any other point. This point here, negative 3.33, 18.51 should have a corresponding point of 3.33, negative 18.51, which it clearly doesn't. So this is neither even nor odd, just based on the visual of the graph. The cube root of x, by the way, in Desmos, when you do a cube root, you have to do a 1/3 power. The cube root of x gives this graph, and this graph is, in fact, the graph of an odd function. Every point over here, let's say 4, comma 1.59, has a corresponding point of negative 4, negative 1.59 over there. That is what it means to be reflected through the origin. If I draw a straight line through the origin and then extend that line out the same distance the other way, we hit that point. So for instance, 8, 2 should have a corresponding negative 8, negative 2. That's what it means to be odd. So this one is reflected through the origin. Some people say it's symmetric through the origin or symmetric with respect to the origin as well. So that language also exists. So h of x in this case was symmetric through the origin. On the next page, we had f of x is equal to 1/2 times the absolute value of x plus 4. And when I look at this, we can see that it's symmetric with respect to the y-axis. And therefore, this is the graph of an even function. Quantity x minus 2 raised to the 3rd power was the expression for g of x. This is obviously not symmetric with respect to the y-axis because I don't have over here corresponding points. It's also not, excuse me, it is also not symmetric with respect to the origin because like this 4, 8 should have -4, -8, which it doesn't. So this is neither even nor odd based on the appearance of the graph. And then h of x is equal to -1 over x. Well, that is symmetric through the origin. If you look at every single point, like -0.5 comma 2, if I go through the origin, I should get a positive 0.5 comma -2, which I in fact do. So every point is reflected or has a corresponding value through the origin. Now we've seen both the graphical approach by plugging in -x into the function. I misspoke. Now we've seen the algebraic approach, which we found by plugging in -x into the function. And we've seen the graphical approach where we just graph the function and look at corresponding ordered pairs. So either way you can use to find if a function is even or odd, or neither. Now, if I know that a function is even or odd or neither, then if I know some features of a function that's even, I could find other points on that function. Specifically, if I know a function is even, then I know the point x comma y will have a corresponding matching point -x comma y. If a function is odd, then x comma y will have a corresponding point -x comma -y. So that's what example 12 asks us to do. It says, assume that I know something about my function. First off, assume that I know f of 3 is equal to 4 and f of -2 is equal to 7. Therefore, I know the function goes through the point 3 comma 4 and the point -2 comma 7. If this function happened to be odd, what would f of -3 be? What would f of +2 be? The same thing, if this function were even, what would f of -3 be? And what would f of 2 be? If you want to try this on your own, just push pause on the video. I'll do this in a couple of seconds. Well, if my function is odd, since normally when I plug in 3, I get an output of 4. If I plug in a -3, I should get the negative of the output when I plug in a 3. So I should get a -4. The same thing is true if I do f of 2. If my function is odd, then I should get the negative of f of -2, which I know f of -2 gives me a 7. Therefore, I should get out a -7. On the other hand, if f of x is even, if my function is even, then I know that if I plug in 3, I get the exact same value out as if I'd plug in a -3. So f of -3 is going to be the same as f of +3, which is a 4. Similarly, if I plug in a 2, I get the same thing out as if I plug in a -2 if my function is even. And since I know that f of -2 is 7, I get out a +7 when I plug in a +2. So if I know a couple of points and I know my function is odd, then I can find other points on the graph. If I know a couple of points and I know my function is even, then I can find other points on the graph. By the way, a function cannot be even and odd at the same time. So you can never have even nor, you can't have both because that would violate the idea of being a function. So for instance, 3, 4, you'd have to have this for odd, but you'd also have to have this for even. So you're saying f of -3 is both -4 and +4, and that would violate this thing being a function, right? So can't be both even and odd. Function can be odd, or it could be even, or it could be neither, but it can't be both. Let's do another example. In this case, instead of having the graph of, having points on the function, let's say we have a graph of a function. Now, interestingly enough, we have to make sure we have a 0, 0 there. So this must be a piecewise defined function. And we have this piece of the graph here. We're going to say if f of x is even, then what is f of -1 and what is f of -2 given this graph? And then we'll do the same thing if this is odd. If the function is odd, we'll find f of -1 and f of -2. Push pause on the video if you'd like to try this on your own. So here's our graph, and we're going to start with the even case. Now, just lay this out. If we're thinking of it, basically, if we're doing an even case, we're going to mirror image across the y-axis. And I can't draw it very well right with my cursor there, but we can see we get this kind of W shape. I'm going to clear that out because I'm really only focused on these 2 points. F of -1, what's going to happen at -1? Well, I can figure that out by reflecting the point 1, -3 across the y-axis. That's going to get me to the point -1, -3. F of -2, well, here's f of 2 at 2, 0. Reflect that across the y-axis, and I get to -2, 0. So f of -1, basically all I'm saying is that f of -1, since it's even, is the same thing as f of 1. F of 1 looks to be a -3, and so f of -1 is a -3. F of negative 2 is the same thing as F of 2. Looks like we're going through the point 2, 0 there. And so F of 2 is 0. Therefore, F of negative 2 is 0. And we do the same, not the same, but a similar thing when the function is odd. When the function is odd, F of negative 1 will be the negative of F of 1. It looks like F of 1 is a negative 3. Therefore, the negative of negative 3 is a positive 3. We would reflect it through the origin, and it'd be way up here somewhere. So we get a negative of negative 3, which is a positive 3. Interestingly enough, if f of x is odd, when I plug in a negative 2, I get negative of f of 2, which is the negative of 0, which is just 0. So notice that reflecting through the origin and reflecting across the x-axis is the same when we're not reflecting across the y-axis and reflecting through the origin gives me the same thing when I'm on the x-axis. In other words, negative 0 is the same thing as positive 0. So there you go. That's how we can use whether a function is even or odd to find other points of interest. That concludes this video on transformations of functions. We saw a lot of transformations of functions, how to graph a function given those transformations, how to look at the graph and find the equation using those transformations. And then we spent some time on even and odd functions.